sure so with YouTube, I think there's always like a few second delay. So I always like to make sure it actually pops up.
Yeah, I was watching. I feel like I was watching the Seattle data guy,
Oh yeah,
the episode with him,
yeah, yeah,
and
yeah,
I think he had it open on the side also just to make sure that it was working. I think.
yeah. Cool. We've popped up, so we are live. Hello, everyone. We're gonna wait, I think, just a minute or two before we really get into the content. But if you're watching live, let us know in the comments or in the chat where you're watching from. It's always really fun to see kind of where everyone's tuning in from. I'll type something there. I see some people joining.
I actually thought this was a Seattle-based meetup.
Well, it used to be,
Oh, it used to
but
be. Okay.
before the pandemic, it used to be a Seattle-based in-person meetup, which is cool. But with like a lot of things, we've gone a little bit more virtual. Tune in from Seattle. Hello, I'm also in Seattle. Kevin is not in Seattle.
I'm in Orlando.
So across the country. This is why it's fun doing virtual too, though. Like I miss in person stuff, but it's so awesome to bring in guests from all over and reach audiences from all over. Cool. I think we'll go ahead and get started with intros, and I'll give a couple more minutes for people to join. So, my name is Sage Elliott. I am the host for today's Robust and Responsible AI event. In general, we're a community of AI and machine learning practitioners, researchers, designers, and pretty much any type of role working in the field of data or ML or AI. And if you ever want to come on to a live podcast as well, let me know. This is kind of a really fun way to get to know people in the community. And you can think of this as kind of a live podcast. So I'll be interviewing guests starting with specific topics. And then we should have time for maybe some questions at the end. But I also encourage you to post in the chat throughout the conversation and connect with each other. Even if we don't exactly respond to everything, it's really cool to connect with other people in the industry. There's also a link in the description to the Slack channel. Which is, I think, near the bottom, the R Squared Slack channel. So that's a good way to stay connected with people as well, or if you have any other follow-up questions. And like I mentioned, if you want to come on for an event, let me know in the Slack or send me a LinkedIn request and let me know there. And today we have our guest, Kevin, with us, who is going to talk about how to make big data problems small. Kevin, could you introduce yourself and tell us a little bit about your background before we get into the big data topic?
Yeah, so my name is Kevin. I've been in data for around 5+ years now. So I studied civil engineering in college, and then I did some research for the government. And then after that, I kind of didn't like the pace of research, so I decided to become a data scientist. So that was 5 years ago. So I was a data scientist for 4 years. Used a lot of Spark in the last job, and then most recently, I was at Prefect. Prefect, if you're not familiar, is a workflow orchestration company. So I did a lot more data engineering stuff in the last year and a half, open source workflow orchestration. I recently left Prefect 2 weeks ago, and now I'm focused on Fugue, which we'll be talking about today.
Awesome. I'm excited to hear more about it. What was going from data scientist to more data engineering like?
Yeah, so I think um so actually everyone at Prefect, like all the early employees are all former data scientists that are working on like an data engineering tool. And it's I think it works out well because there's a lot of empathy for the end user. But I think in general, like I don't know if people here will agree with me, but I think like you start off as a data scientist, but uh there's no one like before the existence of the machine learning engineer role, it was kind of up for grabs who would do the deployment stuff, Dockerizing stuff, putting it out in production. And it just so happened that like the more technical data scientists would end up doing this. So I found myself in that situation where it's like I was, I guess, one of the more technical data scientists on the team. So even though I was a data scientist in the last job, I found myself doing a lot of like CI/CD, testing, Dockerizing, stuff like that. So it was a pretty natural transition to go full on data engineering. And I kind of prefer it over data science. I mean, not that I have issues with data science, but I kind of prefer the more like the data tooling space.
It's okay to prefer things, you know. I don't think anyone's gonna get too mad in the chat. I could see that being interesting, like going from the data science side and then getting more into the engineering piece. So I like I've done similar things in my career as well.
Yeah,
Um,
yeah.
all right, so before we get into how to make big data problems small, for those who don't know, at a high level, what is big data?
Yeah, so I've recently been reading the Fundamentals of Data Engineering book by Joe Rice, right, and Matthew Hosley, and they have a good way to frame it where they said like back then, maybe 5 or so years ago, or even more, big data actually meant like massive scale of data that took specialized tooling to handle, right? But nowadays, like because tooling has been democratized to some extent, and now the bar to work with big data is much lower. Big data kind of just became data engineering. Like it's like the term big kind of faded out because everything is big these days. But in general, when I talk about big data, I think it's basically, hey, the workloads that you're running don't fit on a single laptop anymore. So that there's two forms of that, right? One is like, hey, it's taking too long to process, which is compute bound. So like, hey, my pipeline is taking 6 hours. It's running, but it takes 6 hours. How can I reduce that? And the other one is like memory bound, right? So hey, my data is literally 16 gig, but my laptop's only like 8 gig. I need a bigger machine, right? So anytime that you need to extend from your single machine to something more, then I would say that that's big data.
I think that's probably a very good definition of it. So what's the journey of a data practitioner when the data gets too big? So like you might start and you're developing on your single machine, or a couple or something, and then at some point it's going to get too big for that. And what are the strategies to deal with that?
Yeah, so what I frequently see is that, I mean, and this is a tooling issue, right? So the frameworks that you use for like your local machine are different from the frameworks that you use for big data, right? So on my local machine, maybe I'm using Pandas, and on the big data side, I'm either using Spark or Dask to leverage a cluster, right? And the problem here is that if I wanted to migrate my existing Pandas code in order to bring it to Spark or Dask, it would involve significant rewrites. So the most common thing that we see people do is like, for example, they have a 16 gig virtual machine running their production workloads, and then all of a sudden 16 gig is running out of memory. They'll just bump it up to 32, and then 32 fails, they'll just bump it up to 64, right? And that's what we call vertical scaling, right? We're just like beefing up the underlying compute. Of course, this is not the most efficient use of resources, right? Because yes, you got away with without rewriting your code, but at the same time, maybe you have a 64 gig machine, but maybe your pipeline is running for like 1 hour and only 10 minutes needs a 64 gig, and maybe the rest of the time you don't need as much resources, right? So overall utilization is low when you do this vertical scaling. The other thing, and another thing, is that even if you're using something like Pandas, right, which tends to be single core, it's not natively parallelized code. So even if you bump up to 32 gig or 62 gig, you're not necessarily using all of the underlying compute CPUs, right? So combined with that, what we also see a lot of people doing is what I call like the do-it-yourself parallelism, where they kind of bust out the multi-processing library or like the concurrent library in native Python. And what they start doing is they start like sharding their data. Like I have this like 100 gig data set, and I'll make like 101 gig files, and then I'll parallelize the functions and then spin up other Python jobs. So, and they do it themselves. And this kind of tends to become unwieldy and unmaintainable because like there's tends to be like one person in the organization who knows how it was done and they did everything right, and then everyone else just kind of has to follow along that framework. So before you end up doing the do-it-yourself parallelism, I would highly suggest asking if it's possible to do it in like, even if you're not using a cluster, Spark and Dash still have local modes that you might be able to use that to parallelize for you, right? But yes, the two things are number one, vertical scaling, and two, this do-it-yourself parallelism that we frequently see.
Gotcha. Yeah, the do it yourself. I feel like everything always has something that's similar to that as the do it yourself method, and then yeah, there's one person that knows how it works. Also, for anyone
Yeah,
watching, have you experienced that before? I'm sure plenty of people have. Right. So there's the the do it yourself and the scaling. What are some other unique challenges to working with big data?
yeah. So I touched on this a bit, right? Where it's like the small data frameworks, well, I mean pandas, right, that run on a local machine are different from the frameworks that run on a cluster, right, like Spark and Dask. So I mean Dask has some parity with the Pandas API because Dask is built on top of Pandas and built on top of the PyData ecosystem. But even if you're able to port all your code over, like you actually did some kind of refactor, there's still a couple of challenges on the big data side, and a lot of it has to do with the intuition, right? And it's hard that people don't have a baked-in intuition for big data and distributed computing because they're not like they we are introduced to like the data science field with our laptop and like doing things locally, right? So something that, for example, they run into is like a lot of people I see like to, for example, do a sort of data. You just want to say sort this data frame, right? And that is cheap on a local machine. But when you talk about data that's spread across like multiple machines, like you have four machines and you're doing a sort over four machines, now you need to machines need to exchange data somehow to be able to sort your data frame, and that's what we call a shuffle, right? So there are a lot of like seemingly trivial operations in in the local computing setting that become that have a lot of overhead in the distributed computing setting. So instead of doing something like sort, can you just do some aggregation instead before you have to sort, right? There's a lot of things that may be able to speed up your processes. And another thing is like in pandas, there's this concept of the index, right? So you can say, hey, get me the row, get me row 1000 of this data frame, get me row 2000, right? But in Spark or Dask, this concept doesn't even hold, right? Like, what is row 1000 when your data frame is spread across four machines, right? So the concepts are not necessarily one to one. And a lot of times, when the people experience difficulty when they hold that local data mindset and apply it to a distributed system, right? Um, so, and then aside from the intuition piece, of course, there's a lot of like overhead having to learn Spark, having to learn Dask, right? In the most recent Stack Overflow survey, like it's like Pandas usage was like 35% and Spark usage was like 5%. So there's still obviously like a tooling, like a tooling gap in terms of like adoption, like people knowing Spark, right?
Yeah, that makes a lot of sense. Do you have any favorite kind of resources for people who need to start learning those tools?
Oh, that's another challenge in itself, actually. When I mean like, when I mean like, pandas itself well documented, no problem. You go on Stack Overflow, you should have no issue. But then like when you deal with like Spark or Dask, I would say documentation tends to be much thinner. I mean the actually the Dask docs is good, Spark docs, but then Dask docs is really good. But I find people don't really read the docs; they just try to learn with like Stack Overflow instead. But in general, like of course, like there's gonna be much less responses. In fact, sometimes I see wrong responses, right? So it's like finding material where you can learn is a challenge in itself, for sure, 100%.
Yeah, and at least I feel like there's a lot more data engineering content than there was like 4 years ago,
Yeah,
which is nice.
definitely. Definitely, yeah. That's certainly nice. When I started Spark like 3, 4 years ago, everything you Google, you'll get Scala results back, and that wasn't so helpful, right? But now I think Databricks said something like only 20% of the Spark users are still on Scala. or
Oh wow,
30%.
interesting.
Yeah. It's all Python and SQL now.
I mean,
Yeah.
it makes sense. Like, most of what I've seen has usually been in like PySpark, but yeah, that's I didn't even think about that switch just from the language alone in like 4 years.
Yeah.
But yeah, I used to work at a place where we would train a lot of data scientists, and then it was interesting just seeing the industry switch of like we want to hire all the data scientists all the time to being like, all right, we have enough data scientists now, we need data engineers.
Yeah. Well, I guess I have seen other organizations do this also, where like the data scientists have data engineering tasks, and like I remember, like I think Stitch Fix had a blog about this, where they kind of want their data scientists to be half data engineers and half data scientists. What's your opinion on that? And having like like an all-in-one, not all-in-one necessarily, but a data scientist who can handle more of the engineering responsibilities as well.
I think that totally makes sense, but obviously it would depend on the team and the structure of your company. Many people I know, I feel like, kind of fall into that role, and but often they're at a little bit of a smaller company. I think it's super valuable to know, even if that's not like your job of implementing those things for the company, but understanding, what the data engineer is doing either before you're consuming data or what they're going to do with your data afterwards. I think is probably pretty important to know and understand.
Yeah, because I was most recently at Prefect, right? And Prefect is a data engineering tool, but it is a data engineering tool designed for data scientists and for data analysts, right? So I think that there are even like if you talk about like other orchestrators that are coming up, they like for example like I see Flight, and they have like baked in machine learning also into their workflow orchestrator. So I feel like a lot of these like engineering tools are also being designed with data science use cases in mind, and it's very easy for data scientists to adopt. And there's like ML specific orchestrators too, right? Like ML Flow, Kubeflow, like stuff like that. I mean, I don't know about Kubeflow, but at least MLflow, it's easy enough for a data scientist to adopt. So I think that the tooling is also going in that direction, where like data scientists can do more with having to learn less, right?
Yeah, yeah, and let us know if you're watching live too in the chat. Your opinions on that. Of you kind of said half data scientist, half data engineer. I think is how they were referring to
Yeah, yeah,
it. um, we'll move on to the other question while people are responding to that. So how can people start solving these big data problems and make them smaller? The title of this talk.
yeah. So I mean, of course, we'll talk about Fugue later, but before we go there, I want to frame something here, right? So when you want to make a big data problem small, the goal here is just really iteration time, or I mean execution time. Eventually, when you have to run in production, execution time will be fixed, right? But the main thing that you're trying to drive is iteration time, and big data iteration is hard, right? So a lot of times we see number one, people are testing against the cluster. I'm testing Spark code, I'm spinning up the cluster, running it on all the data, right? And even if you test Spark code locally, Spark code, the JVM will take like 20, 30 seconds to spin up. So it's kind of painful to just keep iterating locally as well, right? So number one is iteration speed. And then number two also is maintenance, right? If you have a lot of Spark code written, you kind of need somebody who knows Spark to be able to maintain that code, right? It takes like Spark specific knowledge. And then a lot of times, what I see people doing is they try to I won't say over optimize, but they optimize their Spark code or their big data code, and maybe they reduce like execution time by 2 3%, 5%, but the code base, they added like 100 lines of code, for example, to get that. And I think a lot of times people are in this mindset for big data that we need to optimize everything, whereas there's still a lot of value if you maintain more maintainable code and just have code that you can easily revisit and easily tweak in the future, right? So a good example of this is something like if you're if I mean I guess people may not be familiar with UDFs, right? User defined functions. So the goal of UDFs are like, hey, I have this piece of Python code, or I have this piece of Pandas code that's already written. How do I bring it to Spark or Dask? And then what you do is you wrap it as a UD. You have your function, you wrap it as a UDF, and now you can apply it on Spark. People, there are a lot of people who are kind of allergic to the concept of a UDF. They think, and there's, I mean, there is fair reasoning, right? Number one, they say Spark treats it as a black box, so Spark cannot optimize it. If you use native Spark code, Spark can optimize it. Use a UDF, you can't. But on the flip side, though, if you think about testing, right? If you can test a UDF that's written in Python or Pandas without Spark, you can just unit test that very easily, right? So there's a trade-off here of keeping code like easily testable, easily iterable, and not having to bring it to native Spark. And I'll give you a good example here. So I was two jobs before Prefect. I was in a payroll company, and payroll's business logic is basically a lot of if else's. If the person is hourly, if the person is salary, if they have overtime pay, if they have, there's just so many if else's. And one of the reasons I started in this rabbit hole is because we had to re-implement a lot of that logic, that very specific business logic for both Spark projects and for Pandas projects. So my thinking was, how can we consolidate it in a way that we can just centralize the maintenance of that logic in one place, and then we apply it on Spark or apply it on Pandas. So when we talk about making big data problems small, it's number one, let's like we have to be open minded to how can we make testing easier in general. And it's not entirely true, and we'll talk about Fugue there. But uh, when you use a UDF, testing becomes easier, maintenance becomes easier, right? And then of course, making big data now that you have like small data tooling, you can couple that and test it on a Pandas data frame as well. You can test on small data. So the goal here is that you can test your logic on one piece of data, one partition, and when you're ready to bring it to production, you can just scale out and say run this whole thing on Spark, right?
Yeah, that makes a lot of sense. We have a good question from the chat, which is what would you consider to be the minimal stack software tools that a data scientist slash data engineer should know for distributed data science work?
Yeah. So thank you for the question, Christopher. I'd like to think that Fugue is related here because and we'll talk about Fugue soon. But so number one, if you're doing anything distributed, I don't think it's a stack that you have to be concerned about. I think it's the concepts, the fundamental concepts that you have to be concerned about, right? Because as long as you're familiar with the fundamental concepts, they will be consistent across whatever framework you're using, whether that's Spark or Dash or through Fugue, right? But in general, you need to know about number one, let's say partitions. What is a partition? How do these partitions move around? How is data stored? And you just need to know that. You don't need to know how to manipulate them. And then number two, um, y- uh, well, there you just need to know the inconsistencies. Like for example, a big one is like schema inference. In Pandas, it's very cheap. You just infer the schema when you load in the data, and that's very common because, like for example, CSVs don't hold schema. So whenever you load it in Pandas, it's common to have everything as a string. But in distributed systems like Spark Dash, schema inference can become very expensive. So it's best practice to be explicit about schema. So there's for your question, Christopher, it's not about the stack. It's just a lot of these like details that you have to be aware of in order to use distributed computing effectively.
Awesome. Thank you for the answer. And then I'm excited to hear much more about the project you're working on that you've mentioned a few times. Could you
Yeah,
dive in and tell us about that and how it can kind of fit into that the stack or how it solves a lot of the problems we've talked about?
yeah. So I hinted this a while ago when I first started in this like big data journey. The problem that I saw was we were re-implementing the same piece of logic once or twice. And I kind of mentioned this that Spark has UDFs in general that you can port like Python or Pandas logic to Spark. What I didn't mention is that there's a couple ways to do it. So there's UDF, Pandas UDF, map partition, apply in Pandas, map in Pandas, and all of them have their own requirements. And it's very it's a lot of burden for the user to have to learn which one I have to use, right? So one of the things that Fugue does is we provide a very minimal interface over all of those, and as long as you like, we're the ones who figure out which is the best one. So you give us your logic, and we'll figure out what the best way to execute that on Spark or Dask is, right? Another thing is that if you use the native Spark interface, for example, use something like map in Pandas. Map in Pandas will normally require you to write two helper functions, right, or three helper functions. So just by making your make just by following best practices, keeping your code lightweight, you get penalized on the testing side. Now you have to test two or three more additional functions. So on the Fugue side, what we do is we eliminate all of that boilerplate code also. We're open source, by the way. So Fugue in general is an open source uh, abstraction layer that takes your small data code and brings it to big data, Spark or Dask or Ray in the future, right? So we are the ones that port your code, and because we heavily test on our side, on the Fugue side, on the Fugue package, you only need to worry about testing your function, your Python or Pandas function. And what this does is by relying on Fugue to just say, hey, change the engine to run this on Spark, or just change the engine, run this on Dask. What that lets you do is you can focus on your business logic rather than the execution piece. Because to Christopher's question a while ago of what the minimum stack is, we think our thinking is that data scientists should not need to know distributed systems very deeply to be able to port their code over. They just need to know the minimal like interface so that they can, because data scientists really want to focus on their key skill, which is handling that business logic, right? And once they can establish that business logic, then they can bring it out to Spark or Dask just by saying run this on Spark, run this on Dask. The second thing, which is kind of uh, very elegant, is that if you think about SQL as a language, SQL is scale agnostic by nature. Your size of the data will not affect the SQL query, right? It's very simple. Select, star, group by, where, stuff like that. And uh, what we want to do is we want to make an agnostic representation of your logic, and then you can say run this on Spark or run this on Dask. So we also have a SQL interface alongside the Python interface, and that's just so people can choose whatever interface they want. So if you use Spark, Spark has a SQL interface. There's already a package also called Dash SQL, which is now maintained by the NVIDIA guys. So it's very common to run SQL on top of these distributed computing engines. On the Fugue level, we have Fugue SQL that maps onto those, but there will always be one-to-one parity. We always support, like, you want to run in Python, you want to run in SQL, the SQL just gets converted to Python at the end of the day. So what we want to do is we want to allow users to express their logic in whatever way is convenient for them, in whatever way they know best, and then we'll handle the bringing that execution over to the distributed setting.
Very cool. And by the way, links to the project and the Fugue Slack channel are in the YouTube description. So if you're watching on YouTube Live, you can go and I think join the community there and look at the docs and the open source project. Do you have any other resources that maybe we didn't link to that you think would be valuable for people to kind of get started?
The Slack is the GitHub is will have all the resources. The tutorials is correct. And if there's anyone who has any questions about distributed computing in general, very happy to chat. You can reach me on the Slack channel as well. If Fugue or not Fugue related, always happy to chat about what you're working on distributed computing wise.
Awesome. And I know we have just a couple minutes left on our stream. Does anyone have any questions for Kevin for anything we talked about or any questions about Fugue? And if you have anything else you want to talk about, Kevin, you can also mention it here.
Yeah. I just want to say that, a lot of people who we work with, they kind of like they're running into these bottlenecks. My Pandas code is taking over an hour, 2 hours. How do I parallelize it? Or I need to start Spark, or I need to start with Dask. How do I get started with that? And they don't know where to start. We're very happy to help these kinds of people, and we can do it very minimally through the Fugue interface. So very happy to chat with like if you're wherever you are in your distributed computing journey.
Very cool. Let me wait a minute, see if any questions come in. Otherwise, we'll probably go ahead and wrap up the stream. And thank you so much for coming on, Kevin. It's really exciting to hear about all the stuff you're working on and your journey leading up to the point, all the various pieces you've gone through to understand what data engineers need or what data scientists need out of distributed systems.
Yeah, thank you. Thank you for having me, and thank you everyone for watching.
So I said, excellent conversation. Appreciate it. Thank you. Not a question, but thank you for the feedback. Awesome. Well, it is 10:30, so I think we're gonna go ahead and wrap up. And thank you again, Kevin. And I'm gonna go ahead and end the stream, everyone. Thank you for tuning in and watching. If you do have any questions later, feel free to message us either in the Robust and Responsible AI Slack or in the Fugue Slack. Thank you again, and I'm gonna click end here.